Welcome to my new calculus channel. My name is John Gabriel, and in today's lecture I'm going to tell you about the ideas that led to the development of the new calculus, or rather to the discovery of the new calculus. And we'll continue to see how I started off with the mainstream calculus and ended up realizing that it was flawed, and eventually I came to the realization of the new calculus. Let's begin. So I was around 13 or 14 years old when I began to teach myself calculus, and eventually I did take real analysis at university, and I spoke to professors, and I realized that they didn't know anything more than what I had originally found out in my study of calculus and also in my discussions with other academics. So the book I taught myself calculus from is this book here, and one of the diagrams that I first saw and really sort of intrigued me was this particular diagram here. And the reason is that I encountered these terms, infinitely small, and points moving. Points don't really move. Then also the fact that what's being said here is that there's a limiting position, but it says the limiting position happens when B moves to coincide with 0. Well, if this B coincides with 0, not with 0, with O, if B coincides with O, then this arc length is 0, and so is, and there's no chord. So, in other words, you're looking at that 0 divided by 0 position. That's the limiting position. So these things just stood out like a sore thumb from the first time I saw this. But being an abstract learner, I simply decided that I was going to, for the time being, accept the facts and move on. Otherwise, I'd never have been able to figure out the rest of what was coming. Now, calculus has nothing to do with limits. And as you'll see, let's just close that current tab. I've actually shown that at this point here, the finite difference isn't defined. And remember, I told you in a previous lecture why you needed to have this condition greater than 0. It's because you need a hole there. And of course, when you define the derivative, it must also be defined there. But for the purposes of this very definition, there must be a hole. So it's a lot of screwed up logic, totally flawed. And you can't use this very definition until you know the value of L. And of course, you can't know the value of L until you use the bogus first principles method, right? The first principles method is the one that was taught to you at university, where you have an expression in x and h, and you simply set h is equal to 0. And that's how you get your guess, which is L. And then you verify it using this verifinition, not definition, but verifinition. So, as you can see, it's all nonsense. It was never rigorous. And so these things really troubled me when I was 13 years old. And moreover, what troubled me was how did they come across the connection between the derivative and the integral, okay? And that was, to me, what I called the missing link. And I had an idea that the mean value theorem had something to do with it because it looked so simple, so refreshingly simple, but I had no clue. So I did a lot of studying, and I eventually came up with, I also studied down Alisi, some parts of it in Latin, which I taught myself, and I came up with some really astounding results, as you'll see in this chapter here. And these results actually connected the derivative and the finite difference, and also I have a formula which connects all three. This particular formula here will connect all of these, and this will work up till the second derivative. If you modify the formula, it can work up to the nth finite difference. But in this case, it'll work for the first and second, and that's about as far as it goes. But this was a connection, so I could see that I'd established a missing link, but I didn't understand the fundamental theorem of calculus. Many of my professors had no clue, and I was kicked off ResearchGate, internet site, because some academics there didn't like my ideas, nor my new calculus, which I discovered. It was their loss, of course. In any case, even with the missing link no longer missing, the fundamental theorem cannot be understood without the knowledge of the new calculus. One requires a deep and profound understanding of the mean value theorem. So I carefully studied all the proofs of the mean value theorem, most of them being a shameful joke. And I set out to prove it using the tools of analysis, but there was something I could not do. And given the fact that there is no such thing as a real number, I had to somehow get around that by creating what I call a positional derivative, the concept of a positional derivative. And I explain what this means in my document, and I have also explained the concept of a positional derivative in the chapter that came just before this one. I also discussed it in the previous video, which was lecture 9, I think. So, as you can see, I also discovered several other theorems. One of them that I shared with you in the book is the average Son Theorem. And it's quite fascinating in the sense that if p is equal to 1, it reduces to the mean value theorem. And if p is greater than 1, it's really just the definition of the function f of x. Okay. So now the new calculus is based on solid analytic geometry. Okay. It doesn't use any ill-formed concepts such as infinity, limit, or infinitesimal, or anything else of the sort. And there are no inconsistencies. So, for example, there is never a derivative at an inflection point, at any inflection point, okay? Unlike your bogus calculus in which you have tangent lines at inflection points, and sometimes they have a slope or a derivative, and other times the curve or the particular function doesn't have a derivative. So your calculus, your mainstream calculus, is hopelessly broken beyond repair, with the results generally being correct, but the formulation absolute rot. And the new calculus was born out of the frustration of me trying to understand all these things. I also explained to you in one of the previous lectures the essence of the mean value theorem, and the mean value theorem was really the glue that made everything possible. So in the next lecture, I'll discuss the new calculus derivative and show you how it works in a completely analytical geometry setting, and that it doesn't require any ill-formed concept. And so I hope you've enjoyed this little presentation, and that you'll join me again for the next lecture sometime soon, I hope. This is a New Calculus channel. My name is John Gabriel. Till next time, goodbye.